So you can look at the solar forcing. And at least over the last 2 million years, it's thought that the Milankovitch cycles are what's really causing it, mostly driving when we get glaciers and when we go to interglacial period, for the Pleistocene glaciation. Let's see. Oh, wait a minute. There we go. Oh, and there should be audio with this. Hang on just a second. I'm not used to having to plug this. Let's see if this works. Let's see. Are the speakers not on? The speaker's on, it's just not playing back.
Check the wall panel behind you.
And it gives you the same thing that's here on the, let's see, volume speech. Well, I've got the volume turned all the way up here. And the volume's up on my laptop. Interesting. Okay. Anyway, this is an illustration. I'm not sure what the problem is with the volume here, but everything seems to be working. It seems to be set up right. But this is just basically illustrating the different orbital cycles here, what you're doing relative to the sun. Project power video. Well, this is always fun. You guys don't know how to do this, do you? You have no clue. You're just sitting there. No, not us. Don't call on us. Okay. All right. I give up. No mas. But you get the idea. These are just the orbital cycles. The sun. Okay. Finish the video. Let's move on to the next one. This is why I hate embedded videos. Those are glaciers, those are movies of glaciers. We're going to skip that. Okay, so, because without the sound, they don't make much sense. Anyway, it's not a big deal. It's just pretty pictures of glaciers if you're flying over them. So, when you have an ice age, one of the key characteristics of an ice age is that you have large continental glaciers. Okay, large ice sheets that cover continents. That's sort of the definition of a glacial period. Okay, and we'll talk that there are different types of glaciers. But first, I wanted to just talk about what is a glacier, what does it look like, and how is it made. So basically, a glacier is just that. It's accumulated snow. You have a period where you have snow's coming down, it sits on the ground, and then conditions are right. You need to have conditions that are right so that the snow can stay on the ground year-round. Okay, it needs to be cold enough that the snow doesn't go away. So so that you're able to accumulate snow year after year after year. So it never goes away and you just pile and you make a bigger and bigger and bigger pile of snow. Okay? Now what happens to that snow is that as you start piling the snow up, the pressure at the bottom of that snow pile increases, right? This is like going underwater, right? If you're at the top of the pool, you don't feel any pressure. As you go deeper and deeper, you feel more pressure. If you go deep enough, you need to start using dive helmets and that sort of thing to keep the pressure from causing havoc in terms of your blood system. Same thing in the atmosphere, right? When you go up in a plane, you're going from down on the ground where you have the whole atmosphere weighing on top of you to up in high altitudes, and you get lower pressure and your ears pop because there's less atmosphere on top of you weighing you down, so you feel less pressure. Same thing happens in a glacier. And a glacier is that you sit on the bottom of the snow piles, pile, you're piling more and more snow up. There's more and more weight pressing down to the bottom. As that weight presses down, it causes the snow to recrystallize. Okay, the individual snow crystals, the ice crystals, to recrystallize, and the crystals will grow bigger and bigger. These are bigger and bigger ice crystals. That changes the material property of the snow. So you go from being loose, unconsolidated snow up to the top to being ice down below. You all see this like in piles of snow in the winter when there's big banks of snow down behind you. It actually starts to stick together more, right? So down here you've got ice that's actually coherent. It's coherent, but it's brittle. It breaks when you force it. When it starts to move, it cracks. Okay? When you try to make it move, it cracks. If you continue to put pressure on the snow, so the snow gets piled higher and higher, eventually the stuff at the bottom starts to weaken, and it'll actually deform what's called plastically or ductily, which means that it flows. Okay? It's just kind of like if you take a bar of taffy or something like that, or a candy bar. If it's cold, if it's really cold, and you do that to it, it cracks, right? Whereas if it's only sort of cold, it's warm, do that, and it's sort of, it's all gooey, right? That's the difference between brittle and ductile deformation. So anyway, as pressure increases, it's not temperature affecting it, it's pressure. As the pressure increases to the bottom of the snow, you'll get this layer down here that's the ductile zone, which allows the ice to deform freely. Eventually, what will happen is, as this becomes more ductile, it becomes easier and easier for the ice to move as the pressure gets higher and higher. And eventually what happens is that the force of gravity acting on the ice is strong enough to overcome the frictional resistance of being grounded on the ice, on the rock, and you'll get the ice starting to move. And once that starts to move, once the ice starts to move, then you have a glacier. Okay? And so in cross-section, you kind of see a ductile zone here, a brittle zone up on top, accumulation up on top of that. The accumulation happens up here at high altitudes. Okay? It's where you're adding to the glacier. The glacier flows downhill like this, flows because of gravity. And down here at the bottom, you lose material off the glacier through a combination. It's a process called ablation, but it happens through a combination of melting, you're just taking the ice and converting it to water, the water flows away, or evaporation and sublimation, where you convert the ice to water and then the water evaporates, or you just take the ice and you sublimate it directly to the vapor phase at low latitudes or low altitudes. Okay? And then the brittle zone, so the ductile zone you get flowing in, the brittle zone you'll get cracks in. Okay, so brittle deformation you develop cracks in, and in particular you develop those cracks when you go over bumps in the topography, when the ice has to flow over a bump. It stretches the overlying layer and you'll get cracking as a result. And these things are called glacial crevasses. So you're flying, as you're flowing over topography on the bottom, you'll get those sort of cracks in the top layer. But those cracks won't extend into the ductile layer because you can't crack ductile material. It deforms, it doesn't crack. Okay, so looking at it in reality in terms of some actual glacial features. So here we are up in the mountains, and you can see the accumulation zones are up here at the top. This is what's known as a valley glacier. You're accumulating the snow up here, and then it's flowing down here, down this way. So all of these areas up here where you're piling up the snow, and that's the source for the ice that flows downstream. And then down at the edge of the leading edge of the glacier, this is the ablation zone where you're removing more material than you're putting in, or you're balanced if you're staying still. But on average, you're removing material from this lower range, the ablation zone. This is the front edge of the glacier. So melting goes on. And again, in cross-section, what happens is in the upper brittle zone, you get cracking. The cracking, because you're cold, but you're low pressure. Okay? So you behave brittly and you get cracks that form, particularly as you flow over topography. In the lower region, you're cold, but the pressure is high. And because the pressure is high and you've recrystallized, you can actually flow. And because of that, this is what the velocity looks like within the ice sheet. So you basically have zero velocity down here at the bottom. You get faster and faster and faster as you go up towards the top of the ice sheet. Okay, and then the ductile stuff just sort of flows along with whatever velocity is constant here. The brittle stuff flows along with whatever the top of the ductile stuff is doing. Velocity. So this is an example of ductile flow in a glacier. And you can see in ductile flow, everything's nice and continuous. It's smooth. These little ridges, but you can see that the flow is going this way. You've got a little lobe coming down that way. another lobe over here, but it's moving continuously, like a fluid, like syrup or something like that. Whereas brittle deformation leads to these crevasses. So this is the surface of a glacier that's deforming brittly. And you can see there's just all sorts of cracks all around, right? This is another example of brittle flow in a glacier. And again, it's just all chewed up and you're forming cracks in the material because, again, you're cold, the pressure is low enough that you break, you crack instead of flowing. Okay? And this is just for scale. The geologist on skis in a big glacial crack. These cracks aren't little tiny cracks, they're things that can swallow people up. And of course, when you calve an ice sheet, when you get an ice sheet down next to the ocean and it breaks off in a big chunk, that portion that breaks off in the big chunk is big. Right? So it cracks and stays coherent. It doesn't sort of ooze off the ice sheet, off the continent. It sort of cracks and falls off. And that's brittle. So the icebergs and you can tell by the sharp edges that it's a feature of the brittle deformation at the top of the ice sheet. Okay, so I said there are two different types of glaciers, two principal different types of glaciers. The first type are what are known as valley glaciers. Okay, valley glaciers form in mountain systems, typically in little mountain valleys. At low latitudes, so in equatorial areas, they'll form way up in high altitudes. So if you have mountains in equatorial areas, you'll form little glaciers up in the northern, or towards the tip of the mountains because it's cold enough at the tips. At high altitude, you can actually preserve the snow year-round. A good example of this is Mount Kilimanjaro in Africa, which basically sits within, 2 or 3 degrees of the equator and still has glaciers sitting on top of it because it's at such high altitude. Though those glaciers are shrinking and they're probably going to disappear within the next year. Within your lifetime, the glaciers on top of Kilimanjaro will disappear. So was it The Snows of Kilimanjaro, right? That's the Hemingway novel. Yeah, not for much longer. The other type of glacier that you get is what's called a continental ice sheet. These are much greater in extent. They cover large land masses. These valley glaciers can be a couple of 100 meters thick, and they usually just fill up the valley that they're flowing down. They're not big. They're kind of confined to the mountains. In terms of continental glaciers cover large land masses. They're huge, and they're much thicker. They can be thousands of meters thick. So an order of magnitude thicker than the valley glaciers, and much, much larger in extent. How do we recognize that glaciers have actually gone on, that we've actually had glaciers in the past? Well, there's a lot of geological evidence. You look at the rock record, and there are a couple of different ways in which you can look at the rock record and see evidence that glaciers have been through in the past. One is that glaciers are incredibly, incredibly powerful erosive agents. Ice is a much more potent erosive agent than water, liquid water, or than air. Okay, it's in terms of bang for your buck. You get much more destruction, much more erosion out of ice, and you can leave tons of erosive features. And in the process too, glaciers, if they're eroding rock, they're taking it and they're depositing it somewhere. So there's sedimentation features associated with glaciers too. So you can look at the rock record for evidence of where you've scoured things out with glaciers and where material's been deposited that's related to glaciers. So I'm just going to go through some quick landforms, erosive landforms associated with glaciers. This is a mountain glacier. This is in Colorado, and this feature here. So this is a valley going down off the mountain. This feature here, this sort of circular depression at the top, is what's known as a cirque. Okay, and basically what it is it's kind of like an amphitheater. It's circular depression here that's carved away steeply into the walls. That's an erosive face. So what's happening is that you're forming a glacier here. The glacier's picking up, or it's gradually been picking up and plucking rocks out of the space. In the process of steepen the face, so you get a really sharp, steep face here, and then the glacier takes off from here and moves downstream. In this case, the glacier is mostly gone from this particular area, and this is a remnant feature. You still have some accumulation going on up here. Okay, and then tarns. So when you see a mountain that's carved out like that, that's a cirque. That means there was a glacier there at one point. And a tarn, that's a tarn here, and that's a tarn here. A tarn is a lake. When you take one of these cirques and it gets a little dammed at one end or another for whatever reason, and it fills with water, and the water can either be from melt off, it can be runoff from the glacier, it can be rainwater, it can be river water that gets there, groundwater. But anyway, you take one of these cirques and you start filling it with water, And that's what's called a tarn. It's a lake that's basically formed in the process of circling. And let's see. Lawford wanted me to show you guys this, but again, with no audio, I'm not sure it will play. Yeah, no, it's not going to play. Here's a movie of him swimming in a tarn. For those of you who want to see Lawford in a bathing suit. So another erosive feature that you get near the surface, near the peaks of mountains, is these things that are called glacial horns. Glacial horns are these really sharp peaks that you get in mountains with where you've had valley glaciers. And it's basically what happens is you've eroded away you can think about it, at the head of those cirques, you get really steep walls. And if you get these things forming from multiple angles, you end up taking what might have been a rounded feature initially and carving it out so it's got really steep sides. And that's what's called a glacial horn. It's just sort of the sharpened tip of a mountain. It's been sharpened by glaciers. Okay? So if you have a series where you have two valley glaciers or multiple valley glaciers coming down from a system, so here's one valley glacier, here's another valley glacier, here's another valley glacier, here's another valley glacier. You've got a cirque at the head of each one, right? Where these things come together, so you've eroded this valley out, you've eroded this valley out. In between, you're left with these really sharp ridges. Okay, so this is all sharpened. So it's a really steep side here, really steep side here, and you're stuck between two valley glaciers. This is what's known as a glacial arête. And it's just a sharp ridge. It's a ridge between two valleys, mountain valleys, that's been sharpened by the erosive power of the glaciers traveling down the valley. Okay? When valley glaciers carve out these mountain valleys, so these mountain valleys exist because, well, what's happened is you've had water, you've had rain falling on the mountain, and the rain's eroded down into the mountain. And when rain erodes a mountain and forms a stream, you end up with something that's very sharp like this, a V-shaped valley. It goes like that, and the stream just runs right down through it because the stream incisors the ground as it passes through, right? And you end up with these nice, sharply defined valleys, sort of have a V-shape. When a glacier runs down through the valley, the glacier is just like a snowplow coming down through it. It scoops out everything, and you take your nice V-shaped valley that looked like this, and it becomes a U-shaped valley that looks like this. Just everything in between gets scooped out by the power of the glacier. And you're left with these very characteristic U-shaped valleys, so a big, broad, flat bottom, little tiny stream that couldn't possibly have carved this all by itself. This is all carved out by the glacier, and you get these rounded here, and then you get steep slides, increase in steepness of the sides go up, but it's nice and flat and rounded in the middle. That's a characteristic U-shaped valley for a glacier. Here's another example again from South Alaska. You can see the nice rounded feature here. This has all been scoured out by a glacier moving this way. Okay? One of the neat things about this that happens is, has anybody been to the Finger Lakes or Ithaca or anything in New York? You guys have all seen the Ithaca's gorges, right? Well, the Finger Lakes are actually just big U-shaped valleys. So what happened is you had a glacier that came down during the last glaciation. The glacier came down from Canada, and it eroded out river valleys going north-south, and sort of scooped them and formed these big U-shaped valleys. Okay. But if you had a river that was going east-west, so north-south in the direction that the glacier was going, it just sort of scooped everything out. Everything going east-west, any little tributaries that you had going east-west, it didn't touch. It just sort of went over as a bump because it only scooped out the direction that it's moving. It's the way the erosion works. So what happens is where you used to have these little rivers coming down and joining a big river that was going north-south, you suddenly have scooped out that whole valley, and then the glacier leaves, and you're left with these rivers, the little tributaries that come in high, and now they've got to plunge down into the valley and come over. And that's why you have all the gorges and waterfalls around Ithaca, because of glacial steepening. Those valleys that are left hanging up on the side of these valleys that have been scooped out in the direction of the glacial movement are what are known as hanging valleys. They lead to really dramatic waterfalls. Another good example of that is Yosemite. So the Yosemite Valley has all been scooped out by glaciers, and you have these dramatic waterfalls coming over the sides of the valleys. Again, because they're hanging valleys that were, if the glacier was moving this way and you happened to be a river that was moving this way, that means your valley got scooped out. But any little stream coming in from the side, you didn't get scooped out because you were orthogonal to the direction that the glacier was moving. And so you get stuck hanging up in the air. And then after the glacier leaves, your stream, instead of flowing nice and slowly downhill, go off the cliff and into the bottom. Okay. Another feature of glaciers, another way you can diagnose or a characteristic of a glacier having been present is what's known as glacial striations. Now what happens when a glacier, the ice in a glacier picks up rock as it starts to flow downhill, it can carry these massive boulders on the inside of the glacier in that ductile zone, right? So in that ductile zone, it's carrying these massive boulders, and it'll scrape them along the bottom of the ground, along the bedrock that it goes over. And in the process of scraping, you'll actually carve out grooves in the rock in the direction that the glacier is forming. These grooves are called glacial striations, and again, you've just got bedrock on the ground, you got a big old boulder sitting in the glacier scrapes along, the boulder scrapes along the bedrock as it's being carried by the glacier, and it carves these gouges. So in that case, these are examples of glacial striations from Victoria, British Columbia. And the neat thing about glacial striations is that if you locate them, you can tell the direction that the glacier was actually moving in. So in this case, the glacier was moving in this direction, basically parallel to the striations. These are actually pretty big striations. They can be much smaller. This is another example of glacial striations on a much smaller scale. This is from Yakima, Washington. But again, in this case, the glacier was moving this way. And you can see all these little gouges, right? Rocks came and were dragged along the bedrock this way and left the little gouges. It's another example of glacial striation. So which way was the glacier moving here?
That way.
Kind of this way, right? You can see the channels that were dug out in the rock this way. More glacial striations. In this case, you're running down into the water in this direction here. Okay. And this is a neat rock just because what on earth happened here? I have no idea, right? Because you have you have striations going this way, the left to right across here. You also have striations going up, down, and you also have striations going across at an angle. So this was probably multiple episodes of glaciation that have been preserved in this rock. Slightly different orientation of the glacier coming through. Okay, so in addition to erosive features, and glaciers leave a lot of evidence for themselves in terms of erosion, there are also depositions. So if you're carving out the head of a valley in the mountain and you're creating all this sediment, you're plucking it out of the mountain, you got to put it somewhere. Okay, and where that sediment gets left off, that creates a landform too. So again, you're accumulating rock up here, you're accumulating snow, you're plucking out rock from the mountains and you're dragging it down as the ice flows. You flow over a bump, you form crevasses at the surface, and you're dragging all this suspended load with you, dragging it across the ground, making striations. And eventually, you've got to get rid of that, all the material that you're carrying. And you can think of glaciers at some level are just giant conveyor belts for sediment. So the giant conveyor belts that take material from up here and move them all the way downstream, okay, to the end of the glacier. The rock that gets deposited after, the sediments that get deposited after they've been transported, are known colloquially or collectively as drift, glacial drift. So it's any material transported by a glacier is known as glacial drift. One example of that is what's called glacial till. Glacial till is drift that's deposited as a result of melting ice. So the stuff's being carried along in the glacier, and then the glacier melts, and all the stuff gets left behind because the rock is in there. Okay, and then the glacier brings more, it melts at the edge, drops more off. Okay, so glacial till is really messy. It's unconsolidated because the glacier picks up everything. It picks up sand, it picks up pebbles, it picks up big cobbles and boulders, and it just carries it all together and then drops it. And then when it drops it all in a big mess. So it's all mixed together, all different sizes mixed together, from sand to boulders. Okay, sands and clays to boulders. And that's what's known as glacial till. Some of that glacial till, actually, I mean, this is one of the bigger pieces, right? This was dragged along, this is one of those pieces that was dragged along and created glacial striations. It actually has some striations itself as a result. The stuff getting dragged along actually gets dinged up too, in addition to the bedrock itself. Okay. This is an example of glacial till. In this case, it's much finer. It's mostly sands and clays with a few cobbles and small boulders in it. But you get the sense it can range the whole spectrum. Soil in New England is mostly glacial till, which is why it's so lousy to plow. Because it's not nice dirt like you get out in the Midwest where you can just stick plowing and go forever and not hit a rock. Anybody ever try and dig a hole in their backyard? you can't go more than 6 inches without hitting a big boulder, right, or a rock. And that's because it's all this glacial till. It's all mixed in together. It's not nice, rich soil like you get out in the Midwest where you just have river and sediments. Okay, another erosive feature, again, if you see, depositional feature of glaciers, is these glacial erratics. Glacial erratics are just giant boulders that appear in the middle of fields or in different locations without any, they're not connected to the area, they're not the same rock as what they're sitting on. It's not clear where they came from. It may have come from Canada, it may have come from Minnesota. It's just a big, big, big rock sitting out in the middle of the field. And the idea is this is something that was carried by the glacier, again, probably in the ductile zone, moved along, and then when the glacier left, it dropped, and now you're left with this weird foreign material, typically it can be very large, just sitting in a place where it's out of place. These are glacial erratics from South Africa, in the Sierras, these just big boulders sitting randomly strewn about. This is a glacial erratic in Maine. Okay, when you take these individual when you take the sediments, the till and that sort of thing, the way it's deposited, so not the soil itself, or the material, the sediment itself, but the feature that it's deposited in, they have names. It's called moraines, okay? Or typically, one form of depositional feature is moraine. So what a moraine is if you take a lot of till and you deposit it in a big pile, that pile sometimes is called a moraine, okay? And one example of a moraine is, they have different names. They're named for the different parts of the glaciers where they're formed. A medial moraine, which is this feature here, forms when you have two glaciers that come together, and the sediment that gets stuck in between them forms a little pile of dirt, basically, a pile of till that runs down the middle of where these two features meet and form a medial moraine. So this right down here, this feature, is a medial moraine for glaciers that came down here and came down here. You end up with a ridge down the middle. Lateral moraines are accumulations of till at the edges of glaciers where they've come in contact with the mountain. They've basically been digging out the side of the mountain, and they leave piles of dirt along the side like that, piles of till along the side. So that's what's known as a lateral moraine. An end moraine is a moraine that forms at the end of the glacier. So it's the glacier's moving this way, moving this way, moving this way. The whole time it's got this conveyor belt that's bringing more and more glacial till, glacial drift, dropping it at the end, dropping it at the end, dropping it. So you're piling up all this till at the end, and then the glacier retreats. And you're left with a big pile of till that's right across, that basically marks the end of the glacier. And these are examples. This is an example of a glacier from Alaska, and it's just an aerial photo, and you can see the old lines of till, the old moraines that were formed. So here's the end moraine right here. As the glacier retreated back, it left this big pile of till at the end, and then more piles along the way as this thing retreated back in stages. Every time it pauses, it leaves a big pile of stuff. Okay. Recessional moraines. So this is an example here where you have a recessional moraine. Recessional moraines are just that. So there's a terminal moraine, which is an end moraine, which is the maximum extent to which the glacier went. The glacier got this far and no further. And it just sat there where it's like it doesn't want to retreat, doesn't want to advance, it's sort of balanced, you're piling up more material. Okay, but that's as far as the glacier went. That's called the terminal moraine. It's a type of end moraine. Another type of end moraine is what's known as a recessional moraine, which is as that glacier retreats, it doesn't just go back like this all the way. It goes and stops and starts. So it's here at the terminal moraine, then it backs up, oh, it pauses a little bit, maybe it goes forward a little, pauses, but around this point, and it's dumping off material here. And then it goes back a little further and it dumps more material here. It goes back a little further, it goes and dumps material here. Those, between the terminal moraine and the head of the glacier, all these other end moraines along the way are what are known as recessional moraines, and they're formed as the glacier retreats. Okay? So this is just an example here. There's a U-shaped valley here, U-shaped valley here, and let's see, this is the lateral moraine here, this pile here between where you had a valley, glacier come down this way and a glacier came down this way, and this pile in between is the lateral moraine that formed at the intersection of those two glaciers, and this is in Owens Valley, California. This is a lateral moraine along Rock Creek, so in this case, the glacier came down this way and left this lateral moraine where it hit the mountains along its edge. This is another example of the lateral moraine here. It's along the side of the mountains here where the glacier met the side of the mountain, and it left this pile here along the bottom of till. This is an example of a medial moraine here being formed, right? Right down, you can see the dark line down the middle as this glacier and this glacier come together. can form that. This is another example of a medial moraine here. Kind of looks like a time-lapse photograph, doesn't it? That's flowing. See the glacier flowing here, the glacier flowing here. And in between, you get these moraines piled up on the edge of each glacier, the glacier that form this medial line of till in between. This is another example. You can see medial moraines forming here, medial moraine forming here, medial moraine forming here, as you have a series of valley glaciers. And it's just it's like rivers of ice, right? They're coming down, they're little tributaries coming down to the mountains, meeting the main line of ice going that way. Okay. There are one final form of landforms associated with glaciers, and these are typically associated with continental glaciers, large-scale glaciers. So this is an example of the Wisconsin glaciation. This is the Laurentide ice sheet, the maximum extent of ice during the last glaciation. And you can see it hit Massachusetts, New York, and all of that. At the edge of a continental glacier, you'll have a lot of runoff, a lot of water running off, right? And you'll have melt ponds here. You'll have glacial lakes that form from melting water from the glaciers. Little river deltas. You have rivers draining the glacier from out beneath. You'll have ice blocks that calve off and fall into the lake like that. And then when the glacier retreats, it leaves a whole bunch of landforms showing that the glacier was here once and now it's retreated. And these are the landforms that you see all over Massachusetts. Okay, these are all things that you see locally. So in particular, if you look, so on the map, the orange area here, this is the end moraine for the last, these are two end moraines, well, an end moraine and a recessional moraine for the last glaciation. So the last Wisconsin glaciation, the last pulse of the Wisconsin glaciation, the glaciers ended up here. Long Island, most of Long Island, all of Martha's Vineyard and Nantucket and Block Island, those are all just moraines. It's unconsolidated sediment dropped off by the glacier, and then it retreated. And most of Cape Cod is also, the soil at Cape Cod is mostly sandy, right? And it's just moraine, it's till. So these are the last moraines. Drumlins. Drumlins are features. Drumlins are really neat. Drumlins are little hills that form, and they're rounded. So they've got a steep side in one direction, and then they're kind of flat and rounded like that. They kind of look like the back of a spoon if you turn a spoon upside down. This is a cross-section of one. So here's the steep side, a topographic map. Steep side here, and then a long, shallow slope here. They tend to form in fields, right, that are all accumulated together. And they're formed by the idea is that they're formed by the glacier moving over the land, and then if it hits a knob of bedrock that doesn't want to erode, it's just like water flowing around a boulder in a stream. The ice will flow around the stream, and you end up depositing sediment on top of that knob, and they have very characteristic shapes. They tend to form in fields, and the directions tell you the direction that the glacier was moving at the time. Kettles are another feature. Kettles are formed when you have blocks of ice that break off from the edge of a glacier and get buried in sediment from the glacier. So you've got a region of ice that's packed into sediment, and then when that ice erodes, you're left with a hole. And that hole, it's got steep sides, and it can fill with water, from rainwater or from river water if you're below the water table. The hole itself is what's called a kettle, and when it fills with water, it's called a kettle lake. These are examples of kettle lakes from Cape Cod, but there are also kettle lakes all over, like Walden Pond is a kettle lake, and Fresh Pond over in Cambridge is a kettle lake. These are very common in this sort of area where we were covered by an ice sheet last time. Another form that you get, two forms here. One's what's called an esker, and the other one's what's called a came. Eskers are these little bumps. Sorry, no, cames are these little bumps, like this, these random little bumps. What happens there is if you have a crevasse on the surface of a glacier, a crack that forms on the surface of the glacier, that fills up with sediment as it's carried down with the glacier. The crack forms in the glacier, it fills with sediment, it's carried along, it's carried along, it's carried along, and then when the glacier melts, it drops that whole pile of sediment in one place. You end up with all these little piles, like that, like that, like that. Those are what are called cames. And then there's this feature right here, which is what's called an esker. It's this long, windy thing. And what eskers are is they're, again, mostly sand in smaller sediments. They're sinuous, they're continuous, and they tend to align themselves in the direction that the glacier was flowing. And the idea here is that what these were deposited, they're sediment deposits that came out of rivers that were meltwater rivers that formed underneath the glaciers as the glaciers were melting. So you'd have these little areas of the glacier where water was coming out. In the process, the sediment would accumulate in that, and you'd be left with that. So this is basically looking at the drainage system for an old glacier, along the base of an old glacier. You also form glacial lakes along the perimeters of glaciers. This is glacial Lake Agassiz, which was in Canada, named after Agassiz here. There used to be, at the end of the last glaciation, so you go back about 12,000 years ago, and this was all one big lake. It was all meltwater from the Laurentide ash that was retreated. And what happens there is you've got this large lake that eventually it's just formed with meltwater. When the glacier disappears, there's no longer a source of water or enough source of water to maintain the lake over time. The lake evaporates off, and you're left with these nice areas in the middle of all these fields where you have nice flat sediments and it's lake beds. Okay? Same thing happens around Albany in New York. You've got Albany is a very flat area around Albany. It's the remains of glacial Lake Iroquois. These are examples of glacial lakes right at the edges of glaciers. Pluvial lakes are small lakes that form at the edges of glaciers due to precipitation, rain falling at the edges of glaciers where you get large changes. If you think about it, if you're going from land where you've got warm air to over top of a glacier where you've got very cold air, that transition from warm air to cold air leads to a lot of precipitation at the edges of a glacial field. And because of that, if you have any depressions in the land nearby, you'll form these short-lived pluvial lakes that evaporate off and leave a flat bed at the bottom. And you're all looking at the clock desperately like, please let us leave, please let us leave. Okay, when these things evaporate off, they leave salt flats, okay? And that's as far as I'm going to go, so you guys can all take it up with Wofford on what? Tuesday. All right, take care.